Today we will embark on the hypothesis testing. What does this mean? What is it about? To be able to understand the concept of hypothesis testing, maybe I'll just make a quick recap of what we did last time. One of the things that we did last time was to estimate a certain parameter. I suppose you wanted to estimate mu, which is a population mean. You did it through a point estimate, which will give you a single value, or you would obtain an interval estimate, which will give you an estimate for a certain range of within a certain range of values. Okay, within a certain range of values. Now, I suppose you got something like that. You are uh, estimating a certain claim amount made by individuals for a certain insurance policy. All right, and you get something like this. What you need to understand here is that when you are getting something like that, or you are getting, let's suppose, 12,000 as an estimate, you have to understand that you don't have any prior knowledge about mu, or you do not make any assumption on this mu. You do not make any assumption on this mu, but you are just estimating and getting a values directly. Now, what is the difference between hypothesis testing and what you have done before? In hypothesis testing, one of the main difference is that now you are going to hypothesize a certain value for mu. You are going to hypothesize a certain value for mu, which is different from what we did earlier. Here, you did not hypothesize any value for mu, you just did an estimate and you were done. But here, you are hypothesizing a certain value for mu. Let's suppose one of the things that you think is you believe that the average claim amount of policyholders for a certain policy is 15,000 rupees, or let's suppose 13,000 rupees. You say that this is your belief. What you are doing here is that when you believe it is like this, it means that you are setting an hypothesis. You are setting an hypothesis, and that's the difference between what you did earlier and what you are doing now. Now you are setting an hypothesis about your mu with a certain value, 13,000 or whatever it is. But here you did not do that. You just estimated the value of mu. That's already the main difference. Now, having understood that difference, we are going to get into other details about this edge. We're going to get into final details about the hypothesis testing, what it represents. Normally, when you refer to a statistical hypothesis, before we talk about a test of an hypothesis testing or a test of hypothesis, we have to talk about a statistical hypothesis. What we are doing is we are not testing any kind of hypothesis, but we are testing a statistical hypothesis. And what is a statistical hypothesis? It's a conjecture, all right? It's like a speculation that you are doing. A conjecture is like a speculation about a distribution of a random variable, which means like, let's suppose you are assuming, let's suppose, it's not necessarily the case, but let's suppose you are assuming that uh, the claim amount is going to follow a certain distribution, let's suppose normal distribution with a certain variance mu, sigma squared and mean mu, okay? I don't think that claim amount will follow a normal distribution, but let's assume it's like that. So what is happening here? You have your two parameters, the mean and the sigma squared. Now, what you are doing when you are doing a statistical hypothesis, you are basically assigning, you are basically doing an hypothesis, a conjecture on the parameter of a distribution. You're doing a conjecture on the parameter. For example, you are saying that you believe that mu is equal to 10,000, you believe that mu is equal to 15,000, or you are saying that you believe that mu is greater than 20,000, things like this. There are different kind of hypotheses that you can set. You can also set things like that. You believe that mu is not 30,000, or you can say you believe that mu is less than 15,000. There are all kind of hypotheses that you can set, okay, for mu. So we are doing a conjecture, a speculation about it. Now, There are two types of hypotheses. There is one that we call the simple and one that we call the composite hypothesis. The simple is the one that completely specify the probability distribution. And if you look at these four different hypotheses that I set, there is only one of it that completely specifies the distribution, which is this. Right? You are completely specifying the distribution. However, for these three here, they do not completely specify the distribution that you have, because you are saying that if you are saying that it is greater than 20,000, you are saying that there are several possible values for this mu. You are saying that there are several possible values excluding 30,000. You are saying here that there are several possible values less than 15,000. So in other words, it does not completely specify the distribution. In this regard, if you look at this is what we call a simple hypothesis, and this is what we call composite hypothesis or a composite hypothesis. This is a composite hypothesis, this is another one, this is another one, and it goes on like that. So that's the idea behind what we call a simple hypothesis and a composite hypothesis. In this course, you will know that we are going to consider only simple null hypothesis when we are doing any question for this module. So we are going to refer for the null hypothesis to be a simple. What does it mean by the null hypothesis to be simple? It means that uh, your hypothesis would always involve an equality. What does it mean for hypothesis to be composite? It means that your hypothesis will always involve an inequality. So what are we going to do in this course? We are going to consider only the null, a null hypothesis which is simple. Now the question is, what is a null hypothesis? And so let me just explain that to you here. We refer to something that we call a null hypothesis and an alternative hypothesis. So let's suppose, to explain that concept, let me tell you something. Let's suppose I say I believe that the average claim amount of policyholders for a certain policy is 10,000 rupees. That is my hypothesis. This is what I believe. Now you have to understand something. In that at some point in time you have your hypothesis very good, a statistical hypothesis has been set, but the thing is you want to test your hypothesis, because when you say you believe it is 10,000, there is no guarantee that what you are saying is right. You might be totally wrong. So you need to carry out a test of this hypothesis to determine whether you are going to reject or not reject. You're going to reject or not reject this hypothesis. That's what you need to decide. These are the only two conclusions that you will come up with for this hypothesis that you have set. But now let's suppose you are rejecting the null. You need to realize that if you are rejecting the null, there is also an alternative. If you are rejecting this hypothesis, let's forget the null for the time being. If you reject that hypothesis, it means that there needs to be a fallback to this hypothesis. There's always going to be a fallback to this hypothesis. So if you reject that hypothesis, you are saying that there is a fallback. What is the fallback of this hypothesis? The fallback, obviously, is that if you rejecting the 10,000, it means that it is not 10,000. So if it is not 10,000, it means that the fallback can be represented by mu being not equal to. And how do you define these two hypotheses? You define one as a null and one as the alternative. And you define it by note, H note, and H1. Now, sometimes some people write it as HA, it's all fine. Okay, so H note represent what we call the null, and H1 represent what we call the alternative hypothesis. So the alternative hypothesis is a fallback of the null. So that's the idea behind what we call the alternative and the null. There is something else that you need to realize is that when you are doing your test of hypothesis, there are two hypotheses set in front of you. You nevertheless always test the null. It's only the null that you are going to test. That is, it's only the null that you're going to test to come up to a conclusion of whether you reject or you do not reject. So you have nothing, it's not about this. You don't test the alternative, you test only the null. That is, your conclusion will be based on the null. If you are saying reject, then the alternative is valid. But if you are saying not reject, then what you claim to be correct is good. So that's the idea behind. Here you will see that there is no issue at all because you are you claim to believe that the average claim amount is 10,000. So your null was mu equal to 10,000. But what about if I tell you now, I believe that the average claim amount of the policy holders for a certain policy is more than 10,000. Suppose it is more than 10,000. This is what I believe it is. So you have an hypothesis that is said to be like this. But there is a small issue that you have to be careful is that I told you something is that in this course we are going to consider only the null which is simple. And you have to understand that you can't consider this as your null hypothesis. Why you can't consider this as your null hypothesis? Because it is not a simple hypothesis here. So if it is not a simple hypothesis, you have a small issue. Let me just erase that and write it down there. So you have a null and you have an alternative. You believe that the uh, average claim amount is more than 10,000 rupees. I told you that the null will always need to be simple. If a null is always needs to be simple, and this is what I'm trying to know, there is a small issue because I always test the null. So what do I do then? The idea is you can't change it. It's always going to be simple. So if you are testing 10,000, you're going to test equal 10,000 here. You can't do anything about this one. But what about this alternative? This is where the whole thing becomes important. Because if you say that you believe that the average claim amount is more than 10,000, if you are going to reject that null through your hypothesis testing, when you are going through the through the procedure that you're going to carry out, if you come up with a decision to reject that null, then what would happen? You need to ensure that what you claim is going to be satisfied, and what you claim is that it is greater than 10,000. So the alternative would then be greater than 10,000. So if I'm rejecting the null, it means that what I'm claiming is okay. But if I'm not rejecting the null, it means that what I'm claiming is not okay. So that's the idea, is that despite that you are trying to figure out this and you can't test it through the null, you can still find it out through the alternative. You can still consider it in the alternative. So, but bear in mind, you are now not testing this. Even this is what your aim is about. You are not testing this. You are still testing mu equal 10,000. That's what you are testing. And in the end, you will either reject it or not have insufficient evidence to reject that. So if you will reject, then your conclusion is satisfied. Otherwise, your claim is satisfied. Otherwise, it's not. But bear in mind, I repeat, you are still testing the null. And then there are a series of errors that occurs. There are two types of errors because when you are rejecting the null, there is an error that may occur is that you may be rejecting a null hypothesis that is true. Because when you're carrying out your test or your procedure, you are going to make use of your sample data for you to come up with a conclusion. Do not reject, do not reject, or reject. That's all what is going to happen. Based on your sample, you will come up to a conclusion whether you will reject or not. So what is going to happen here is that you may be rejecting, your sample may tell you to reject a null, which is in fact true. And if this is the case, you are referring to what we call, you have made an error here, and this is what we refer to as a type 1 error. However, there is another type of error, which is not rejecting a false null. So now you came up to a conclusion, don't reject the null. So if you don't reject the null, but in fact, let's suppose the null uh, was false. If the null was false and you did not reject it, that's another type of error. You need to realize that these are two different types of errors, and they are referred to as a type 2 error. So these are some of the elements of hypothesis, of test of hypothesis. Now, you can go through this on your own. I'm going to come back to that afterward in the next slide. Now, um, sorry, yes, let me just create a slide. Hold on a minute. So, we just referred to the probability of making a type 1 error. We just referred to the type 1 error rather. Now, the probability of making a type 1 error, because given that it is an error that may occur, there's a probability that it occurs. And this probability is what we refer to, is what we denote as alpha, and is what we refer to as the level of significance. That we refer to as a level of significance. Now there is another one that you need to understand, is that there is a probability of making a type 2 error. And this is denoted by, obviously, if this one is alpha, this one is beta. Now beta, we don't really give it a name, but we do have a name for 1 minus beta. 1 minus beta, the probability of 1 minus beta is what we refer to as the power of the test. I would avoid getting into all the details about alpha and beta here, their computation, etc. I'm just going to be very brief about it and mention a few things that you need to realize. Is that very often what we would like is to have a small value of alpha. But at the same time, we also want a small value of beta. That's the idea in the end. We don't want to have a high probability of making a type 1 or a type 2 error. But unfortunately, things are not so straightforward. Very often is that when you decrease the alpha that you have here, there's a tendency for beta to increase. Now, what does it mean by a tendency for beta to increase? If you decrease alpha, the power of the test will also decrease, because if beta is increasing, 1 minus beta will decrease. So this is what happens generally. If your level of significance is decreasing, your power of test is decreasing as well, which means that you cannot decrease that to a too small value. You cannot, for example, decide to say I'm going to put it as 0.0, something like that. You cannot do that. Why? Because if you start doing that, you will have a very weak test. And this is not what we want. We want a test to be, at the same time, have a relatively low level of significance, but at the same time, the test is powerful as well. So we want to have a kind of balance that goes on between these two. This is why most of the time in many exercises, you will see in many questions on hypothesis testing, you will see a level of significance of 0.05 is set. Very often you will see this. It's like a kind of standard that is used, because this value is not too small and not too big as well. So it is a kind of balance that will ensure that your test is generally powerful and your level of significance as well is not bad as well. So there is also other values that are used, like like 0.1, 0.1, and there are values like 0.01. These are possible values that are used, but most of the time it's the level of significance of 0.05 that is used in carrying out a question on hypothesis testing. So this is something that we refer to as a given. When we say the level of significance, we refer to it as a given level of significance. As a given level of significance. There is something else that we call the observed level of significance, which is basically something that we call the p-value, but I'm not going to discuss this here. I'm going to leave this to later. The discussion on the p-value, I'm going to leave it to when I'm going to discuss the chi-square test of association. But for the time being, I'm going to uh, do hypothesis testing in the traditional setting, which is the critical value setting, which you would understand again afterward. So that was a little bit of theory behind the hypothesis testing. Now, what is the next step? The next step is to be able to carry out a question on hypothesis testing. We are going to carry out the test of hypothesis. That is, we are going to carry out the procedure, which are as follows. You need to go through all these procedures as follows. Just understand something. A question on hypothesis testing will, let's suppose if it is like 9 marks I give you. I expect you to have all these different steps mentioned. All right. If I give you 10 marks, things like that, I will expect to give you these 10 marks based on these different steps. If you're just going to write down the null, the alternative, and just maybe do the computation and give a conclusion, you're missing quite a number of important information in your answer, which is going to be described through these procedures. So what I'm going to do maybe is to go through these procedures rather than going through them one by one now. I'm going to go through them through an activity that I'm going to do with you. So I'll do this activity together with you and show you how we answer a question on hypothesis testing based on these different procedures. Here we go. A manufacturer of candles claims that their average life is 9.25 hours. A random sample of 35 candles was drawn from a day's production, and the mean and standard deviation of lives were found to be 8.62 and 0.71. So just understand something, is that the standard deviation of the lifetime of this candle is the standard deviation is 0.71 and the mean is 8.62. Now you have to be careful and understand clearly what are the information given to you in this question. So you clearly see, for example, here that there is a 9.25 which is also a mean, 8.62 which is also a mean, and this one is a standard deviation, and you have a sample size of 30. So let's just write down the information. You have n equal to 35, which is given to you. And then you have a mean here of 9.25. You have a mean of 8.62 and a standard deviation of 0.7. So what is this 8.62? If you read properly, you will see that this 8.62 is based on the sample of 35. So in other words, the information that has been given to you is x bar is equal to 8.62. And the standard deviation of 0.71 is the standard deviation of the sample, which is equal to 0.71. 0.71. So you are not given the true standard deviation, but you are given the sample standard deviation. And then you say, is there evidence to support the manufacturer's claim, which says that he claimed that their average life is 9.25. The manufacturer claimed that the candle is 9.25. So this 9.25 is the claim made on a parameter, right? This is something that is unknown. Normally, you don't claim something that you see. This is an observed value. You are not going to make an hypothesis on an observed value. You make an hypothesis on something that is unknown. So, based on all this information that is given to us, we can start working out this procedure, which states that the first step is to define the term. So, let's define the term here. We're going to write it down. I'm not going to write it down completely. I'm going to write partially, but you can complete it afterward. But just to get you used to the concept of hypothesis testing, what it looks like, and how to answer a question, and also you can continue it later on your own. So the first step is to you define the term. What term? We are testing what? If you look at this question, what are we testing? We are not testing a proportion, we are not testing a standard deviation, but we are testing something that we don't know, which is 9.25. So in other words, you will say let mu, because 9.25 is an average, let mu be the true average, the true average, uh, sorry, the true average lifetime of a candle. Okay, that's the first step. We are done. The next step would be, when you have done that, you need to say, okay, what type of test are you, sorry, the next step would be to state your hypothesis. What hypothesis do you have? What are your hypotheses? Your hypothesis is that is there evidence to support the manufacturer's claim? Your hypothesis is always related to the question itself. The question is there evidence to support the manufacturer's claim? So what is the manufacturer's claim? He claims that the average lifetime is 9.25. So that's the hypothesis. All right. So we will say H is mu, H note, H1, such that mu. We always know that in this course, the mu is always equal. And what about the next one? What is happening here? Mu is going to be what? So mu is equal to what, first of all? Mu is not 8.62. Don't think that because you've seen a mean here, it means that you are going to put 8.62. If you are doing that, it's like you are saying this. This is what you are going if you're doing this. It doesn't make sense. You don't test something that you observe. You test something that you are, which is unknown. So the idea here is to use 9.25. The next step is, of course, this should be 9.25, but what do we write down as inequality? It's based on the question. The manufacturer Kendall claims that the average life is 9.25. This is what he claims. The evidence to support the manufacturer's claim. So it is 9.25, so it's a null already set. So what is the alternative, a fallback? If it is not 9.25, obviously you need to understand that it is not equal to. Please do not look at this value and decide about this based on that. Many students do these kind of things. They look at the sample to decide what the alternative is. Because the sample is 8.62, some people think that it should be less than 9.25 as the alternative. If you think like that, it's wrong. You do not look at your sample when you are stating your hypothesis. These hypotheses that you've set has nothing to do with what is happening in this information here, as from this line. It has nothing to do with this, all right? Because it is only based on information related to the question. What is the question? This. If the question says something, the hypothesis is based on that question. That's all. You should not be looking at this when you are stating your hypothesis. It has nothing to do with that. Just write down this information if it is confusing you. All right. So let me just get back to this. Our first step was to define the term, which we did. The next step was to define the statement of your to write down the statement of your hypothesis, which is done. Our next step is to define our level of significance. As I told you earlier, all hypothesis testing questions are based on the level of significance that is given to you. If it is not given, you take it as 0.05. But if it is given, it's good. You use whatever is given. So now, but I'm not going just to write down the level of significance here and I'm going to finish though. I'm going to write down something. You see, because if you look at the alternative, right? If you look at the alternative, you will see that there are two possibilities for the alternative. Either the value is less than 9.25 or it is greater than 9.25. If this is the case, what happens is that you are carrying out a two-tailed test. We say a two-tailed test is carried out at the 5% level of significance. Sorry, I'm just going to erase that. You can continue it later. A two-tailed test, I'm going to need space for me to write the other parts later on. So that's why I'm not going to write it fully. A two-tailed test is carried out at the 5 with alpha is equal to 0.05 or at the 5% level of significance. When you mention that, this is our third step done. The next step comes the assumption. So we are done with those three steps. The next step comes the assumption. Now, what are the assumptions that you are going to set here? It's just like we did in the course, it's just like we did last week when we studied confidence interval. I repeat, I told you earlier that there are four cases that you will have. These four cases, I just make a quick recap, would be n is large, sigma known, n is large, sigma unknown, n is small, sigma known, n is small, sigma unknown. These are the four different cases that you will have in a question. Now, if n is large, you do not have any assumption as such to do. However, remember that if n was small, you would have to do the assumption of normality of populations. So that's how you decide on that. So here the sample size is 35, which is large, because we mentioned that in this course, we are considering n is greater than or equal to 30 as large. All right. So if this is the case, then we are dealing with a large sample case. So with a large sample case, we'll be more precise with that one. Why? Because that one? Because sigma is unknown. This 0.71 is not sigma, it is S, but sigma is not given to you. So sigma is unknown. Now, if sigma is unknown, we are dealing with this case. There is no specific assumption in terms of normality of population to state. You should not write that kind of assumption. However, you will have to, one of the assumptions that goes everywhere is the assumption of a random sample. You could here come and say, assuming a random sample of candles has been selected, under H note, then we are going to continue. Assuming a random sample of candles has been selected under H node. Now listen to me. This assumption, I'm writing it down here for the sake of explanation. In fact, if you did not even write this down, will not be penalized for the simple reason that in the question itself, it's already mentioning it that it is a random sample. So if you did not write it, it's not a big issue. But if it is not mentioned, it is always good to put the assumption. Under H note. Now you will see that I've written under H note. Why I've written that? Because something follows from that later on. And the other thing is that whatever you are doing, the conclusion that you will come up in at the end of this whole procedure, the conclusion that you will come up is will be either to reject the null or not reject the null. So all that what you are doing is based on the null. So this is why I'm saying under H note. Under H note comes something else, which is the distribution of your test statistic. So we are done with the assumption. I repeat, here you would not have been penalized. You would not even be given marks for that because it's already mentioned. But if it wasn't mentioned, you will have to do it. Then the distribution of a test statistic. What is this? Let me write it down and then I explain to you. Sorry, I'm having a small issue to erase this. Got no idea what's going on, but I'm going to try and write it down above. So the distribution of a test statistic, I'm going to write it down here, is this. I'm going to write it down and then you just, I'll explain to you. So what is our distribution of a test statistic? So what is this distribution of test statistic and why this formula and what is this? So first of all, this is what we refer to as a test statistic. This is our test statistic and the test statistic has a distribution. Now, the distribution that you see here is the normal distribution. Why? Because you are dealing with a normal distribution. Why? For one simple reason that through the central limit theorem, you've learned that x bar follows a normal distribution with a certain mean mu and variance sigma squared over n if n is large. If n is large, this is what happens. So because in our example, we are still dealing with a large sample, and because we are dealing with a large sample, it means that x bar follows a normal with mean mu and variance s squared over root n squared over n. But here, uh, I'm going to represent it in standardized form. Now, what's the idea behind this test statistic that you are seeing? The test statistic that you are seeing here states that if you look at it carefully, you will see that there is x bar. Oh, that's better. Anyway, let me write it down again. Now, the test statistics is showing you the discrepancy between x bar and mu. It's comparing x bar and mu. If you forget that for a moment, the idea is that it is comparing x bar and mu. Now, if your x bar and your mu are close to each other, what we will come up as decision is that we will not reject the null, obviously. But if your x bar is far from your mu, then the conclusion will automatically be to reject the null. So that's the principle behind. It's very simple. But the thing is that it's not going to be easy to determine that. It's not going to be easy to determine that through just x bar and mu. You will need a benchmark to do that. So how would you get this benchmark? The benchmark is going to be based on a critical value that you will obtain from the normal distribution. This is what is going to determine how far x bar is from mu. We are going to explain that in a moment, but the other thing that you need to understand is that this value is going to be referred to as a computed z value. And this computed z value is the value that I'm going to compare with a benchmark, as I told you. Sorry, I just lost the so you have your test statistic, which is looking at the difference between x bar and mu, and this you can it's not going to be helpful if you just look at the difference, because you won't know how far x bar is. It too big? If the difference is too big, is it too big or is it too small? How would I decide if the difference between x bar and mu is too big for me to be able to reject the null? How would I decide that? It's very difficult to determine that just looking at x bar and mu. This is why we use the standardized scale of x bar, like by dividing s over root of n, which was supposed to be sigma, but sigma is unknown. We are going to use s over root of n, and it is assumed to follow a normal distribution. Why? Because of what we explained in the confidence interval. For that specific context we explained earlier, I just explained it to you here. If n is large, sigma is unknown, we are going to use Vz, the normal distribution. For this one, normal. For this one, normal. For this one, however, is the t-distribution. So all the rest are normal. So for any of these different cases, these three cases, you are going to always use the normal. Only for that case where you are going to use the t-distribution, then you would have written it like this. That's how you would have written the t-distribution. So you have n minus 1, which is the degree of freedom, and alpha, the level of significance, if it was to follow a t-distribution, obviously. Oops. Now, I told you that just through the value, this difference between x, y, and mu is odd, but then through this test statistic, it becomes easier. How? Because we are going to make a comparison of what we get over the z scale. You will have a certain value of 0, which is going to correspond to a value of mu on x bar scale. And then what is happening here is that you will need to check where your value of x bar is compared to the mu. If the value is in the extreme, then you will reject the null because it's not close to the null. But if the value is within that range, then you will not reject the null. So you have a certain benchmark here. There is a certain value that you're going to use here, a certain value that you're going to use here as your benchmark to see if this computed value that you get, the computed z, is inside this boundary or outside this. We'll get back to that afterward anyway. So this is what the purpose of a test statistic is about, to compute your to compute your z value. All right. And this z value is going to be used to compare with your critical value that was shown in the diagram here. So this is the critical value. The critical value here, and this is the critical value here. It's a concept that you already are aware of from the confidence interval. So let's continue here. So you've got an idea of what this is about. The next step is to compute. So let's get back to this step. So the distribution of test statistic is done. We are going to compute the test statistic. So to compute the test statistics, we are going to call it a name first. We are going to call it Z because it is from a normal distribution. And how do we get that? It is by taking x bar minus mu divided by s over root of n. So let's do it. X bar minus mu is what? Under H naught. Remember, under H naught, what is mu? It is 9.25. So subtract 9.25. Divide by the square root of s over root n. S is 0.71 and say n is 35. The next step is to do this computation. You are expected to get something, you are expected to get negative 5.249. Right, that's a computed Z that you are going to get. Our next step now, this is going to be a value that we are going to compare with the critical value later on. So our next step is to do the statement of your rejection region. So this is where I'm going to explain now. The statement of a rejection region is what? You are going to write down something. You are going to write down if the Z is greater than a certain value, or if the Z is greater than or less than a certain value. If the Z is less than a certain value, you are going to reject the null. So how do you decide about that? This is why we have said this x bar minus mu follows the normal distribution with mean 0 and variance 1. So you've got your normal distribution. Now you've got your 0. We are stating the rejection region, please. Don't forget that. Now, the rejection region is defined as what? It is based on what your alternative looks like. Your alternative is a not equal to, which means that you are carrying out a two-tailed test as we mentioned earlier. Because you are carrying out a two-tailed test, it means that your distribution is divided into two parts. One on the left and one on the right. So these two regions that I've shaded represent the extreme region. So the extreme region means a value of x bar that is too far from you. All right. But for us, we're not working with value of z, but a value of x bar, but we are working with value of z. If the value of z goes too far there or too far there, it's going to be, it means that there is a huge discrepancy between x bar and mu. In other words, the null is going to be rejected. But let's have a look. So how do we get this critical value? What is it about? I'll just explain it to you and then you can find it out yourself. It is based on the level of significance. The level of significance is 0.05, which means that the area at the extreme is 0.05, both area. In other words, this area is 0.025 and this area is 0.025. So what do you need to do next is to find this value that corresponds to an area on the right. That is an area on the right of 0.025. And you will see that this value corresponds to 1.96. Obviously, this is negative 1.96. So that is the value that is going to be defined as a critical value. If you are using the first table, you will have to look for 0.975. 975. And then you will see that it is 1.96 again. Same thing. Whichever you use, either second table or the first table. If you use the first table, don't forget it's all the area on the left, which means 1 minus 0.025 or 1 minus 0.025, obviously. So this is what I will do. If modulo z is greater than 1.96, we reject H naught. So that is the idea. If modulo z is greater than 1.96, we reject H naught because modulo z is greater than 1.96 means what? Either z is less than negative 1.96 or z is greater than 1.96. That is the conclusion to that. Instead of writing it down like modulus, you could write it down like this, but it's more lengthy. Rather than writing all this, it's easier to write it down like if modulus z is greater than. Now, we are done with almost everything here, and we have only one step left. So let's get back to here. Statement of rejection region is done. We are left with conclusion, which is your technical conclusion and your plain English conclusion, which means that answer the question. Let's get back here. The conclusion is, since the modulus z that you have computed, that is modulus z means what? 5.249. Does it go according to the rejection region? Yes, it is greater than 1.96. We therefore reject the null hypothesis at the 5% level of significance. This is the technical conclusion. So we reject the null hypothesis at the 5% level of significance. And what was the claim? If you have rejected this, the claim was what? The claim that it is 9.25. All right. But what did you do? You rejected the null. So what is happening here? Since modulus z is equal to that greater than 1.96, we reject the null hypothesis at the 5% level of significance. So you see that the rejection or not rejection is based on the null only. So since modulus z is equal to greater than 1.96, we reject the null hypothesis at the 5% level of significance and conclude that what? And conclude that the since we rejected the null, it means that it is not 9.25. So if it is not 9.25, what was the conclusion? The conclusion and conclude that the manufacturers there is insufficient evidence and conclude that there is insufficient evidence to support the manufacturer's claim and conclude that there is insufficient evidence to support the manufacturer's claim. So that is the conclusion that we had to do. So that's how you answer a hypothesis question, testing question. Number one, you define your terms. Number one, you define your term, state your hypothesis, whether you're carrying out a one-tail or two-tail test with what level of significance. Do your assumption. The assumption is based on what I explained in confidence interval. Write down your distribution of test statistic, calculate it, state your rejection region, and do your conclusion. Very simple. That's how you answer a question on hypothesis testing. Now, there is one thing that I want to mention, which I probably did not mention earlier, which is about the conclusion. When we say we do not reject, that's okay, or we also, so here we are saying we reject rather, okay? There's no problem. But what about if you were not to reject the null? You would have said, we do not reject the null, or you would have said, we have insufficient evidence to reject the null. You would say, we reject the null, or we have insufficient evidence to reject the null. So that's how you would conclude. However, I want to draw your attention towards something. Do not, if ever you do not, if you're not going to reject the null, do not use the word accept. Do not use the word accept. Never use the word accept. Don't say we accept the null. You never say that. You always say you do not reject or you have insufficient evidence to reject. Because it's by standard, you should not use the word accept. For what purpose? It's very simple because there is a probability of committing a type 1 error. There is no guarantee that you can say that you accept the null because even that may not be correct somehow. Right? There is always a probability of making a type 1 error, for example. So this is why you should not say accept. You don't bring an affirmation on here. But when you say you do not reject, you are not bringing an affirmation to whether you should take this mu to be equal to 9.25. You are not bringing an affirmation on it. So this is why I say do not use the word accept, but always use the word do not reject. They look the same in English terms, but in statistics terms, they are definitely not the same here. It's just simple to understand. Let's take an example to illustrate that, a real example. If you look at the case of law, is person, let's suppose if there is a case for a certain person and is charged for having done a certain murder. All right. Now, when the judge will pronounce his judgment after having all seen all the evidence and so on, what he will say is that either he will declare the person guilty or he declares the person not guilty. But at no point in time will he say, I declare the person innocent. He doesn't say that. He always say not guilty. Why? Because by saying he is not guilty, he is not confirming that the person is innocent. If you are declaring the person is not guilty, that does not mean that the judge has said he is innocent. It's just that he doesn't have sufficient evidence to conclude he is innocent, obviously. So he has sufficient evidence though to conclude that he is not guilty. So there's a difference, just like here. It's the same analogy that you can look at. Don't use the word accept at no point in time. I do not accept the word accept in your conclusion in exam or class test. So please ensure do not use the word accept. Now, you are going to do this activity on your own based on what I just explained to you. You're going to do this activity as well, this one as well. And by the way, all the activities that I'm mentioning here, even this one as well, you're going to do it, but this one is for proportion. When you're going to define your term, please ensure that you define your, in the case of mean, you define mu, but for this one, you're going to define p, let p be the true proportion, and then you follow the same steps like before, but the only thing is that the some of the changes that will occur is at the assumption stage and also at the test statistic, all right, the distribution of test statistic. This is going to be a bit different. How would you know what it is? Please refer to the confidence interval notes that I explained to you. All right. Then we have the case of comparing two population means. Now, because I've already explained to you confidence interval, I'm just going to be brief about it and give you an idea. All right. For example, here, the difference is that you will not define one term. You will define two terms, mu b and mu g. We define two terms, mu b and mu g. These are the two terms that you define. The other thing is that the rest stays the same. That is, you still have all the previous, you still have all the different conditions that you had earlier. Here, let's take this example. You will define two terms, but there things are going to change. Here, same idea. Here, same idea. The assumption will depend on what you learned in confidence interval for two samples. All right. Sometimes you will have to do three assumptions. At times you will have to do only one assumption. So it depends on what you've learned in the case of confidence interval for two samples. Please see the previous video for more information on that. And then the other thing that will change is this. Obviously, this one will be computed according to that. And this one will stay nearly the same depending on whether you are carrying out a test at the 5% level of significance or not, and then you have your conclusion, which is normal. So what are the few changes? The null H naught is such that mu b minus mu g equal to 0. The difference here is you have mu b minus mu g is equal to 0, and then you have mu b minus mu g is equal to 0, which is, you remember last time we have been testing, we have been doing a confidence interval to see if these two are equal or not. But now when you're doing your hypothesis testing, you will state your null to be equal to 0. You're comparing them against an alternative which will depend on the question. It could be not equal to 0, it could be greater than 0, or it could be less than 0. It depends on what the question is. So you will need to have a look at the question. Sorry, I'm writing on the wrong slide here. Let me get back here. So I'm writing on the wrong slide. H naught is such that mu b minus mu g equal to 0, or h1 is such that mu b minus mu g can either be not equal to 0, or it can be equal greater than 0, or it can be less than 0. It depends on what is being asked here. So I leave it to you to find out yourself what it is supposed to be. The other thing is your test statistic. The test statistic, I would like to remind you something. If you look at it uh, carefully, what we did here, when I drawn the test statistic, I used the point estimate. I subtracted the hypothesized value, or the hypothesized value, which is under H naught mu, as divided by the standard error. So what is the general idea for coming up with your test statistic here? You need to find your point estimate, subtract your hypothesized value, but under H naught you will see that it is always going to be equal to 0 based on what we are doing in this course. We are not testing for any other difference except for 0, right? Because we just want to compare them. So we are not testing any difference as such, but comparing them only. So then you would have only the point estimate divided by the standard error. Now, what is going to be the standard error? I leave it to you to determine the standard error on your own. Then it will follow either a normal distribution, or it will follow a t distribution depending on what is given, as whether the sample size are small and the population variance are known. These are the kind of questions that you need to ask yourself. So I'll leave this to you to continue. I just gave you an insight about it. And then the other thing is you will need to state your rejection region. The rejection region is quite simple. It's standard, something very standard that you need to write, depending on whether you are using the normal 5% level of significance will refer to 1.96, just like the confidence interval case, and a 10% level of significance will refer to 1.645, just like we did in confidence interval. We discussed that. So then you will come up with your conclusion whether the two means differ or not, and then you will answer the question directly. All right. So I leave it to you. These are things I'm not going to discuss because we just discussed it in the previous lecture. And then this is something else that I will leave it to you to do. All right. It is based on two sample. So that's a little bit all that I want to do with you right now. So what I would ask you to do is that all these activities that I've given you, I would ask you to do me the favor of posting your I will create a post on Google Classroom for that, and I would ask you to post your activities there. I would ask you to post your activities on Google Classroom. I will have a look at your solution. I will not be looking at all the solutions in the class, but I will pick a few students at random, and then I will check the solution. And if I see that there are any issues that I need to talk about, I will discuss it in the next week when we are going to meet. Otherwise, there won't be any discussion if you are doing it properly. But if you are not doing properly, I'm going to discuss it in the forthcoming week. Right? So I'll just have a look at a random uh, sample, but you will have to submit it on Google Classroom. So that's all I wanted to talk about. So we'll meet next week, and if there is an issue, I'll discuss them. Bye.